So, okay. Ah, yeah. Okay, better.
Bienvenidos. Entonces, ese es un seminario especial por alguien quien es no simplemente un científico bioinformático, químico muy reconocido y muy erudito, pero también es uno de mis cuates de, no sé, de cantina, entonces desde hace muchos años. Y Peter es de la Universidad de Leipzig, realmente era del grupo de Peter Schuster en Viena, donde conocemos desde hace mucho tiempo. Peter es un frecuente visitante aquí a México y nuevamente al C3, aunque me gustaría persuadirle de venir aquí para una visita mucho más extendida. Pero tenemos el placer de tenerle hoy y mañana. Y entonces va a dar una presentación hoy, bueno, en un cierto sentido, poquito tutti frutti en términos de los temas que va a cubrir. Pero les puedo asegurar que en cada tema que toca, entonces se convierte a un experto rápidamente. Entonces, el título de su plática es From Bioinformatics to Cultural Evolution. Este es un salto bastante grande. Y la otra cosa es que I'm going to tell them that, if you want to just interrupt and ask a question, I can assure you that Peter doesn't mind, because I'll be interrupting and asking questions. Should. I'm sure, right? So. Yeah. They don't. So welcome, Peter, and thanks for coming. And
thanks, Chris, for the kind introduction. I can assure you that coming here for a longer term visit is on my agenda as soon as the problem of having a teenager in school and being kind of tied to the German school system is alleviated in the 2-3 years. So what I want to talk about this morning is in a way a sideline of my work that, however, is becoming more of a focus of my interest, which is the question, which parts of the evolution of culture in society is something that we can understand in just the same way as we can understand biological evolution, and which parts are genuinely tied to specific human intervention or to coincidental actions of individuals that can be identified in or throughout the history. And what I will show you is that, at least in some cultural systems, and I will to a large extent speak about language, but not only, I will also talk about the history of science in the second part of my talk, is that there is a surprising amount of regularity that actually doesn't need individual conscious human action as its explanation. It seems to be collective phenomena that we can describe and understand in ways that are very similar to the way how we would describe, say, behavioral changes, adaptation from bacterial evolution to the evolution of, say, social animals. This is indeed going to be a bit of a potpourri of 4 individual sub-projects that we've been working on that I briefly want to go through. but there is actually sort of a common thread through that, and the thread is basically the idea that we have to transfer, or we can transfer methods that have been around and have been very successful in bioinformatics and computational biology, largely in the area that I'm mostly working with, which really is evolution at the genetic, sometimes also at the phenotypic level, to say something meaningful and useful about cultural systems in the wider sense. This also has to do a little bit with recent developments in computer science, where you see a rise of what's called digital humanities, which is, at least in Europe, kind of defined as application of established computer science methods to support classical research in the humanities, the building of databases, the making accessible and visualization of annotated texts, and so on and so forth. This is not the part that I'm particularly interested in. My colleagues at the computer science department in Leipzig and I are in particular interested in, can we do more? Is there more that computational methods can contribute to different fields in the humanities than just supplying tools for humanities researchers to do, or scholars to do whatever they've done all the time? Is there an add-on that computational methods can bring that to these fields that is actually interesting and can convince researchers and scholars in the humanities to actually go into this area? And this is basically what I kind of phrased here as, is there actually a field of computational humanities, an extension of classical questions, research areas in the humanities that genuinely require data and computational methods to do anything useful? My personal take on that is yes, and this is basically just also ties to my history in bioinformatics. When I started doing computational work in biology and gave a talk at some conference, usually I spent the first 3 minutes to excuse that I didn't do experiments like any self-respecting scientist, but just was playing around on the computer, or even worse, proving theorems. And the next 3 minutes I used to excuse myself that I didn't work on proteins, like everybody knew that this is the only interesting topic, but I was actually working on RNA because we actually could do computations on them. I will not show you any of this bioinformatics stuff now, but that's just sort of a little as a sort of personal background or setup on why we are looking at these 4 topics. The first one is the relationship of sound and meaning in human languages. And there is essentially a dogmatic axiom in historic linguistics that says there is absolutely no relationship between sound and meaning, footnote, with a very small number of very well understood exceptions, which I will explain in a second. But otherwise, this is completely arbitrary, so there should be no signal. Sort of related to that is the question, to what extent can we reconstruct the history of human languages by just looking at their phonetic structure, at the changes in their phonetic structure, which is interesting from the general point of view of what can we say about human language as an obviously sort of cultural system by looking at descriptors that essentially have nothing to do with cognitive function. We don't think about how we pronounce words. This is obviously the phonemic level is a level that has nothing to do with intrinsic meaning of words or anything, so no higher cognitive functions actually go into that. That again then ties in with the question, since we only work with some descriptors that change over evolutionary time, but nobody says that they're in any way causal and we don't really know what the rules are. that underlie these changes, to what extent can you use such data in general to actually make phylogenetic as the simplest way of making a historical inference on these data. And in the last part, I will shift gears a little bit and go away completely from languages and look at the history of chemistry over the last 200 some years, and basically ask what can we learn about the history of chemistry as a culture of chemistry, so a particular science as a cultural endeavor of humans, by just looking at the reactions and substances that people have documented. So are there historically interesting patterns in the way how this space has been explored? So let me start with the first topic, and as Chris said, interrupt me at any time. I'm perfectly happy if I don't get to the end and I have to stop at any time when the majority feels it's time for lunch and you don't want to hear any more of it. So this work on sound meaning associations in natural languages is work with a PhD student of mine, Damian Blasi, who is actually a physicist from Argentina, who developed an interest in statistical patterns of natural languages. All the other guys on the Søren Wichmann, Harald Hammarström, and Morten Christiansen are actually quite well-known historical linguists. So this is a collaboration where we didn't just play around with data and got them published, but this is actually something that was done with a group of linguists who, at least the majority in the field, thinks they know what they're talking about. So the basic idea is in spoken language, there should be no relationship between sound and meaning. As a consequence, of course, specific sounds should not be overrepresented or underrepresented in words that have a particular meaning across a wide area of languages. Clearly, if you look at one particular language or one particular language family, you will see lots of such associations. If you look at written English as a reflection of kind of old Germanic phonetics, you will find KN in a lot of words that have to do with bones and extremities and things like that. So German Knochen for bone, Knie, so knee for knee, and many other examples through the Germanic languages have that. Lots of words that have to do with looking at starting English with GL and green, glimpse, and so on and so forth. So there is a whole group of words, but those are very language specific developments that clearly have to do with the way how you make derivative words in a particular language. But if you would compare Indo-European languages, say, to some Aboriginal languages in Australia, you shouldn't see any of these associations if it is true that there is no intrinsic relationship between sound and meaning. What about very basic things like mama? This is exactly one of the exceptions that linguists are very well aware of. So this is exactly the last line. However, there are a bunch of very well-known exceptions. One is exactly the M in mama, where the psycholinguistic explanation is essentially, well, M and R is the first sounds that physiologically babies learn to express. So this is what they use to address their mother. So this is almost universal that these sounds appear in mother. There is also
a question, Peter, is like, is it known what the progression of sounds is from that point of view? As you say, that there's the physiological capacity to pronounce any old...
there is a lot of literature which I don't really know. So there is a lot of this is known in details, and as far as I'm aware, there is also studies on what is universal across cultures and where cultural differences set in. So, for instance, infants in community-speaking tonal languages learn to parse those very quickly, while we basically don't have, for practical purposes, to that, because we just don't even learn to distinguish these nuances. So there is another example, and this is like small spiky things versus large blobby things. And this is also a known phenomenon. If I ask you in some language that you don't know, which one of those things is Kiki and which one is Bobu, I guess almost everybody would call this guy Kiki and this guy Bobu. So this is actually something also that there is plenty of experiments on this. So there is some general associations with an E sound as a diminutive, which is very regular in German. If you talk to very small children, everything gets an E at the end, and things like this. So these are clearly, so these are the clear exceptions that linguists know of and have described. There's literally thousands of papers on this. But if you look at the basic vocabulary, and this basic vocabulary is essentially defined as the phylogenetically most stable words. So this is the word list of kind of core vocabulary that linguists always use to characterize languages, which is either the 100-word Swadesh word lists, as they are called after this guy Swadesh who first compiled them, to word lists that have about 1,000 words of the core vocabulary. There is only a handful of words in there, like the word for mother, that has this, that sort of can explained or that falls in the category of these few known examples. And the general assumption is that if you leave out 2-3 words from these, there should be no signal of any association of sounds to meaning. And this is actually something that would have been easy to test statistically for a long time, because these lists actually have been around for a long time. And the statistical test for that is not really something that is fancy in any way at all. Essentially, you just count up how often certain sounds appear associated with a particular row in that matrix compared to how often they appear in the whole matrix at all, and you check if you see a signal. And the point is that, so this is the mama example and the gear example that I already managed. So this is just a busy slide that just lists the data that we looked at. And basically we looked at everything that we could get our dirty fingers on, which is word lists from almost 7,000 different languages. What you also have to do is, because languages differ quite a bit in their phonetic structure, in the number of consonants and vowels that they actually distinguish, and so on and so forth. And there's always an issue with orthography. So what we did is we use standard methods of normalizing or simplifying this data to a reduced alphabet where you don't distinguish nuances of certain sounds anymore, and that basically leaves then 34 consonants and 7 vowels. Then if you look at these word lists, linguists also have fun, so they put some artificial languages into these lists. You also so there is actually a word list for Klingon. Since this is completely made up, obviously this is a signal that you don't want to have in there. We also remove all Creole and Pidgin languages, essentially because they have known association effects with phylogenetically very different languages. So they give you a historic signal that you don't want to see. So those were thrown out, and then there is a lot of data garbage. So this is sort of, the very well-known procedure from bioinformatics. The rule of thumb is half of your time you just spend on cleaning the data as they come out of a supposedly well-curated database.
So, yeah, I wonder if it's actually Klingon is of interest. So the thing is that you can look at it almost from a phylogenetic point of view, right? Trying to trace, the relation between meaning and sound. But in some sense, if there's something almost cognitive about it, then when somebody invents a new language,
so we will
you should maybe see the same sort of thing.
We will actually get to that, because essentially you can use the same data just in a different way to reconstruct phylogenies from these languages, and I will show you in the next part on how to do that. So here the name of the game was, what we also do is we look at the existing phylogenetic classification of languages, and everything that is classified is probably maybe somehow historically related. We basically said, okay, this is one group. This only should count once in our statistics, because we don't want to see historical association. We know that there are historical associations that, of course, preserve sounds, but that doesn't say anything whether the association of sound and meaning is arbitrary a priori. It basically only says that if you look at related languages, well, then their sound meaning associations are similar, which is clear because they come from common historic ancestor.
So you're putting in the phylogenetic factor and the geographic factor as two separate labels, right?
Separating that in. So basically, we cut off at the top level of about where we get about 300 independent language lineages, where no respected linguist believe that there is a historic relationship, or at least there is no way of attesting it.
Obviously, there's a correlation between the phylogenetic and the geographic, right?
Yeah. There is, but not always. So we also tested. So you have an effect in language. So languages become more similar when they are actually in contact with each other over a longer time. They just exchange words by borrowing. And they, so when you have languages that have the same sound meaning associations, and and you see that the unrelated languages by phylogeny have a big signal of common sound meaning association that correlates with geography. You know this comes from, or you would suspect at least that this comes actually from contact. So this is one of the confounding factors that we actually had to exclude. And the way how we did that is that we basically said, okay, we look at just geographic distance between the languages, and we ask whether geographic distance is a significant contributor to common sound meaning associations. And to make that long story short, this is one of the tests that came out negative. So basically, geographic association explains essentially nothing beyond the phylogenetic. So if you get rid of the phylogenetic factors, geographic association doesn't explain any part of the variance. It's less than 1% of the variance that you can.
But with the geographic stratification, would you do it now or 1,000 years ago?
It's what you're doing now, because for most of the languages that you don't even have histories that long back. And I mean, most Aboriginal tribes in Australia, for all anyone knows, they didn't move around a lot.
Right, but English as a language has moved around a lot. And some languages moves around as a lot.
They have been around a lot, but it actually also turns out that if you look at an influence of Spanish on, say, indigenous Mexican languages. In this respect, this is basically nil. So we did check for the kind of colonial
That's very asymmetric,
languages
right?
as well.
Meaning, hey, you know, the conquering language enters in, well, it's like Norman going into Anglo-Saxon.
So
Anglo-Saxon into French, right?
English is a very special case in that, because English for that for the purposes of that study, one should actually just kick out English, because it actually pretty much falls into this category, except it didn't completely erode its grammar. English is one of the very few language mixtures where actually you have a significant contribution of both the Germanic and the Romance root that go into the core vocabulary. For almost all other language contacts, all other languages that borrow a lot, they do that kind of at the fringes of their vocabulary, but the whole point of looking at this core vocabulary, which basically contains things like designations for your close relatives, basic objects like stones, rivers, mountains, so lots of physical objects. This is the part of the vocabulary where you very rarely borrow from other languages, even if you're conquered by somebody.
So you are focusing more in these human universals that,
Yes.
Among other things, many words that are human universals, meaning that is common to all cultures, as you said.
So this is
at the
exactly
beginning, as sun, moon. But there are others like the integer numbers, 1, 2, 3, 4. That's had some special.
Numbers are not in there. Or most numbers are not in there. I think
as far as I
2
know,
and 3 or something like that is in there.
As far as I know, as a human universal in terms of numbers is only 1, 2, and 3. 4, 5, or 6 is already not universal.
And it also turns out that numbers have a tendency to get borrowed and exchanged if you have a lot of trade connections and things like that. So there's there's a huge literature and endless idiosyncratic stories on why a particular concept is included in the core vocabulary and others are excluded, sometimes based on idiosyncratic stories that linguists know. So this was basically
other way to put it is these 6,895 words are.
No, this is not the number of words. This is word list.
Word list.
I deliberately didn't. So to be precise, I called it word list because this is the raw data. So this contains, at the end, we wind up with 4,500 word lists. So after we throw all the crap, and they really belong to about 4,300 languages. The rest is dialects. So there is 4 or 5 languages for the major German dialect groups in there, for instance. And I think there is also a couple of English language ones. What we are looking at here indeed is basically the question: is there any global pattern that is visible across all languages? And what you get out of this. So I gloss over the boring thing on how we teach the statistics. This is basically what you find out, and so this is the most strong associations for whatever. So the plus means there is a positive association. It's much more likely than you would expect to see the term "you" in ash, in the term for ash, across all languages. This is just an example that does not pertain to Indo-European.
But the thing is that you're restricting that Indo-European languages.
No. This is exactly for everything,
Yeah, but the thing is that
the point is these associations are the signals that you get as overrepresented association if you look across all these 300 independent language families. So that means you will see a lot of them that actually are there in many languages, but just happen not to be there in Indo-European. So this is not a universal, every word for ash has a U, but what this says is, and in this case, it's basically about 70% of the language families have a U in there, and U is actually not that frequent.
But ash is, in some sense, more universal than you. What do I mean by that? He's like you, as you would pronounce it in BBC English versus et cetera, right?
Yeah, so,
I mean, there's a spectrum of views, right?
This K sound in the term for bone, for instance, is something that's universal.
Yeah, but the thing is that, you're saying K, right? But the thing is that a precise K, as you would pronounce it in a certain, form of a certain language, once again, Queen's English or whatever it would be, is not exactly the same K.
No, it's not.
As a sound
it's not
as
exactly
in another
the
language,
same K,
right?
but
so you have to make the right identification.
So you have
that's a K rather than a
this
C or something,
this is
right?
something that that phoneticists have been playing around with for a very long time, and there is a very
there's a mapping there
well-established history. There's basically a tree that kind of maps what is a variant of a K versus a G.
That's right. And the thing is, what you're hoping is that the distributions don't overlap too much between one of those things and another, right?
So, and then you have some of the things that, like the M for breasts, that all is the same thing as the M for mama. Wherever that U comes from, that's actually even more frequent. And then you also have negative associations. You have sounds that are very strongly underrepresented in certain terms. This was also something that we were So this is actually a fairly common thing because of this known psycholinguistic or actually language acquisition association between mother and the M. This term is actually not in there.
It's like the concept in English. Not one of them agrees.
Yeah, so this is actually what one of the
French or Italian or Spanish or Chinese.
So,
right?
so what I think one of the only ones that's left is the T in stone. But this also has to do with massive recent phonetic changes in English, even relative to the Germanic or Romance ancestor, that has eroded a lot of these terms. So the L in tongue lingua is actually something that's almost completely universal, probably because it started with so this is also something that you see almost everywhere, except in basically part of the Germanic language where we have tongue, Zunge. So the interesting part is that in these 200 top words, so this is actually a third of the core vocabulary that has these massive associations. And this is not like small 5% effects. This is like more than half of the languages have it.
So what do you do for overrepresentation, underrepresentation of languages? So see, like New Guinea has hundreds and hundreds and hundreds.
The only what we did is we normalized so that every language family, every one of these 300 independent lineages just gets a total weight of 1 when you sum up the signal. So in the Germanic, actually, even though this is a huge family with lots of different languages, only comes 1/300 in the whole signal. So this is basically all the tests for confounding factors, so geographic nearness, phylogenetic correlation. Then the reviewers also made us check whether there is any correlation with the particular position in the word, or the size of the number of phonemes in the word, and so on and so forth. And essentially, whenever so the way how you test it is basically you put the confounding factor into a linear model and ask whether you get any weight on it. And the answer is essentially you don't. It explains minute fractions, less than 1% of the total variance in the data. So there's just nothing there. So the take-home message of that is, unfortunately, this convenient axiom that sound and meaning have no relation, and therefore you can do cheap statistics when you work on language evolution, because there are no priors that you would have to measure, unfortunately, is false. This is a little bit annoying, but otherwise, it also implies actually an interest in research agenda that some of our linguist friends are actually pursuing, and that is, what are the explanations for these associations? How can they be explained? Is there psycholinguistic experiments that actually support certain associations? Does that have something to do with language learning? So at least this study stimulates quite a bit of work in that direction, which we essentially know because lots of people cite this thing not only to say that we're stupid.
You can imagine that it's a useful thing, right? I mean, the point would be is that you can that there's a relationship between sound and meaning, because if you just take language per se in the sense of I either know the meaning of the word or I don't know the meaning of the word, end of story, right? There's a set of symbols, and so it's blank for one person and it means something for another. If you've got a relationship between sound and meaning, it can mean that you don't need to know the yes or no of the exact word, right? So in other words, it's like Kiki and Bauba. Well, I know it's this sort of thing, right? Even if I don't know the exact representation, I know it's that sort of thing just by the sound. Eminently useful. If you think of like Kikis are dangerous and Baubas are not so dangerous, in the sense of just the sound of it, then that's actually useful.
There is some correlation with the drone or the house, or
there is some.
We don't know that. So,
for instance, Ma is because this is perhaps the simplest thing to pronounce or say.
There is in very early language acquisition, this is certainly physiological constraints, which is why they are, which is sort of the easy explanation on why they are universal across humans. Later on, so this Kiki versus Bauba example is one that doesn't have any reasonable physiological explanation, but there is something very deep in our cognitive apparatus that just likes to make this mapping. We don't know where it comes from. It's just something that languages do. So I have no explanation for that.
I guess we have one of the leading experts on vocalizations of some primates, this Gabriel. Maybe you want to comment something? Maybe you know a lot about these things. He has done vocalizations in vervet monkeys and spider monkeys, and this has to do with anatomy, or no comments?
Well, I think it's very hard to establish the meaning.
Well, in terms of function, yes. In terms of the effect of a vocalization on others, for example. But here we're talking about symbolic meanings and semantics, and that's very controversial to speak about semantics in animals. So if you're talking only about the association between the morphology and anatomy of the vocal tract and the acoustic structure of the vocalizations, clearly there's a lot to say. But from the acoustic structure to the meaning, that's a whole different
or just
thing.
to the function, if you don't want to use meaning in a symbolic sense. In the case of animal vocalization.
Well, you could speculate about some aggressive vocalizations in which the fact that you open your mouth to vocalize, you probably show in your teeth. And in those cases, there could be a clear association between the meaning or the function or the effect of those vocalizations on others and the way that you're producing it, in the sense that you're showing your teeth at the same time as making a sound. So that could be an association, that's clear. And those have been studied in chimpanzees, for example.
Okay, so the next topic is to look at language evolution at the phoneme level, where the main goal really was, can we just compare phonemic structure, so sound structure, as a way to reconstruct language phylogeny. This is very much a study that was in its beginning motivated by asking, can we do the same thing that we do in bioinformatics also for natural language data? So the idea in bioinformatics is you have all these sequence data of corresponding genes. We just make alignments of genes, and the more different the sequences of these genes are, the more distant is the phylogenetic relationship. So you should also be able to do that with words. So we just take the sound structure of words, try to build alignments of them, and then use these alignments to make inference of the relationship between languages. And the trick here is how to do these alignments of words under the assumption that in the beginning you don't know anything. So let me just jump over this. This is actually not so interested. So what you do in phylogenetic reconstruction, usually you want to have some sort of a distance measure between sequences, or count the minimum number of mutations or edits, or you have probabilistic approaches. So once you have the data, there is a zillion of different statistical ways of inferring essentially the same thing, which is a tree of languages that you want to have at the end. And the question that we have essentially is, does this also work for languages? Of course, in a sense, something like that has been done more or less by hand, just without the computational machinery behind it by historical linguists anyway. Since the brothers Grimm, we know that words in related languages, from Sanskrit, Old Greek, Latin, to German, in particular, again, the ones in this core vocabulary that we looked at before, are often very similar and clearly related. It's actually interesting to know that the first phylogenetic tree was drawn by the Grimms for languages rather than by Darwin for the origin of species. It's basically just that for whatever reason, evolutionary biology developed much more of a mathematical framework, and they are also much more easily picked up computational methods to work on the data than what was the case in historical linguistics. So what's kind of interesting is that is to look very briefly at how historic linguists versus computational approaches actually look at the data. So the classical approach in historical linguistics is you have a bunch of dictionaries, you pick a bunch of examples of words out of that. You begin initially with essentially guessing which words could be related with each other. They are then compared. What linguists are essentially obsessed with is finding sound correspondences. So regular changes of individual sounds between different languages. So from Latin to Germanic, for instance, you have a P to F, pater to father. Transition with P to F is one of the classical Grimm's laws. So it's one of these very, very regular changes just between the Indo-Germanic, Indo-European source and Germanic languages. So once you have identified the sound correspondences, essentially you ask whether your guess is for phylogenetically related words, which linguists call cognates, actually hold up under these rules, under these transition rules. You update these correspondences, and at the end of the day, then you basically ask, where do I see more or less correspondences, and this goes around and around until basically you have convinced all your objectors who don't like the history of individual words. Another way of doing that essentially is to get a phylogeny out of the language is to say, okay, all we're interested in is finding what are lexical cognates, so what are words with the same meaning that are actually historically related, so that have corresponding sound structure. And then what is suggested to just not look at all the details of sound correspondences and whatnot, but basically to just ask between any two languages how many phylogenetically or by ancestry related words with the same meaning have they preserved. The less words they have preserved, the further they are away. So this is kind of what you do in phylogenomic approaches when you just make phylogenies based on gene content, right? You just ask how many genes do two genomes have in common. The more genomes they have in common, the more closely related they are. There is also completely statistical kind of black box methods, and you have a method that very much depends on the sound change. And what we were interested in basically in the beginning, can one more or less build a pipeline like you do in bioinformatics, right? We have a bunch of data, we have a computational procedure that runs through. Can we essentially automatize the work of a historic linguist? So is there enough signal for the computational methods that we have to pick up all these sound changes and so on and so forth?
But the data in that sense is all written as opposed to sounds.
So this is also an infinite discussion with linguists. If you talk to a real linguist, they tell you never ever can work on actual written text because there's all the difficulties with orthography, and in some languages really are hopeless in the way how they are written. English is actually not so bad because the orthography essentially just represents an older stage of the language. But some languages are basically unusable. Irish is written with all sorts of extra letters that mean something that's not the sound in there. So this you really cannot use. Yes?
What about this?
Machine learning or artificial intelligence is a whole new field. It's impacting this in natural language processing and
It is so. Probably a lot of these things you could also set up as machine learning problems And part of this really is machine learning, except that we don't call it machine learning because mostly we really do classical statistical inference because we actually want specific parameters that we can interpret. But cognitive recognition, for instance, is an obvious machine learning problem. And you can train machines that will do that very well. It's basically just we want more. We also want an explanation why this thing is a cognate that we can then go and sell to a linguist and say, listen, this is a cognate because this thing has exactly those sound correspondences that we statistically get from our data. So this is maybe a little bit of a philosophical point, but worth mentioning here. My original upbringing is, scientifically speaking, is chemistry and physics and things like that. So I like mechanistic models, which basically means, I'm not looking for the theory of everything, but for specific processes, I want to have a model that essentially reflects what I or the community knows is the structure of the process and that leaves parameters to learn in that, rather than basically just learning an input-output relation and not caring where it comes from and what internal structure it has. So for me, this is the difference between just a machine that predicts, which can be valuable, and sometimes it's the only thing that you can do. We also do that in bioinformatics a lot for things that where we don't have a clue how it works. But once you have an idea how things work, there is no good excuse, I think, to use a completely amorphous black box machine instead of a machine that actually has the structure that you know should underlie the process that you want to model. And the difference is essentially whether you can interpret the parameterization that you have learned or not. At least in the moment, we don't have any cool automatic methods that take a neural network and explain what the neural network is actually thinking. I mean, people are actually working on that, also in the Max Planck Institute that I'm affiliated with. So Jürgen Jost's group is actually working quite a bit in that direction. And there's also people in the math department who started to work on understanding what exactly these learning algorithms are really doing. So there is progress in that field, but in the moment that we can just train a deep learning machine and then basically tell our deep learning machine analyzer to please explain to us what the underlying model is. So just very briefly how this looks like. So what we do in molecular biology, we have this notion of homology, which I take to be similarity by common descent. So you get these sequence alignments where you have sequences, this is a particular RNA, doesn't matter, where you just basically have sequences from related species that have a lot of common positions, and there is also a lot of insertions, deletions, changes in the letters that have accumulated over time. And you can actually do conceptually, you can do the same thing with in this case the word for star across a number of Indo-Germanic languages, and so if you kind of know the rules on how these languages are related to each other, essentially you can actually pretty much see what the correspondence looks like. This stuff at the end really is frozen grammatical endings that have been added at some point. This Greek A or the Spanish E in the beginning is also a relatively late addition that was added for basically phonetic rules in the language that essentially you have in any of these words that started with an ST in Latin. And then what you also can see is where there is a lot more variation in the vowels than in the consonants. This is a general pattern that's essentially also universal across languages. And essentially, you can use this to start learning these alignments. So in biological sequences, this is all relatively simple because underlying processes. This is basically mutations. And as long as we look at nucleic acid sequences, for all practical purposes, all mutations are equal, or if you want, transitions and transitions should slightly different probabilities. So in biology, our problem is that sequences are very long, and we don't really have to worry about the scoring system on what are the exact exchange rates between individual letters doesn't really substantially what is the alignment that you get out at the end. Linguistic data, unfortunately, are very different. The words are short, and transition rates are certainly not equal. They are not equal between different types of letters, and they are in particular also not very different between particular combinations of letters, and they depend on which individual language families you look at. In this case, it's sort of easy because at least for the consonants, they like to be conservative in this particular example. All the languages agree that an S should be an S. But if you go to Germanic versus Romance, you have immediately Grimm's law and the P versus F, which should be the identity, while P versus P actually is not an identity anymore, so it's not the largest similarity. So you have to learn the scores for the alignment. You have to learn the exchange rates actually from the data, and that's kind of one of these classical hen and egg problems, right? So in order to learn the exchange rates, we need to know the cognates and we need to have them aligned. Once we have good alignment scores, we can align the words and then check if the alignment score is better than what you would expect for the alignment of a random pair of words, so we can actually also identify the cognates. This turns out to be a relatively easy system or thing to do if you start with word lists, because word lists are already filtered so that all the rows in the word list are words with the same meaning. So within these word lists, cognates are highly enriched, because if you look at one language family, and this kind of comparison only makes sense to do within one language family. If the languages are completely unrelated, the best thing that you can hope to get out is essentially reconstruct this sort of a priori associations of some sounds with the words. So it's not interesting, gives no phylogenetic signal. So you do that, of course, only within the language families rather between them. Within the language families, because you have the cognates so highly enriched in these rows, a dirty trick works. In the first step, we just distinguish vowels and consonants. So just build a binary pattern. Then we align these binary patterns, and then we just count in these binary patterns how often we find the correspondence of particular letters. And we cheat a little bit because since completely regular sound changes across the whole phonetic system are relatively rare, we actually just at this stage give an additional weight for having identical matches. So you do all that since you ask. This is not orthography usually, orthography that one can read it, but normally the actual data that you work is phonetic transcription of that, usually in a simplified phonetic system. So where you just have one K sound, for instance, and not three variants of that. So what you do is you do this kind of pre-alignment just on identities, consonant, vowel matches, and we basically forbid vowel to consonant matches except for L and M. And from these data, you then estimate just log odds scores for substitutions. So very classical statistics from pattern matching, and then you just iterate a few times until nothing changes. It actually stops changing after 2 or at most 3 iterations. And then you have a nice alignment score that you have learned for a certain for a pair of languages. Yeah, so this is just the number voodoo, so Grimm's law, sound changes. The alignments, of course, we calculate by dynamic programming. In order to learn context dependence, we also did a little bit of this stuff. So our first pipeline essentially was, we start with pairwise alignments, we cluster the words, the sound changes by alignment scores, use similarity scores to throw out stuff that doesn't fit, and then we build multiple alignments so it actually gets better. You basically correct errors by not only comparing pairs, but by actually doing a consensus comparison of several languages, which is exactly also what what is done classically in linguistics. That gives you the sound correspondence sets, and then you iterate the whole thing. And at the end, you evaluate that, and the real evaluation for the examples that we did was actually ask domain experts on whether our cognate assignments make sense. And we looked at 2 language families where I guess everybody will believe that none of the people who were working on that have any clue about. One is the Mataco-Guaycuruan language family, which is spoken by a few small tribes in the area of the Iguazu waterfalls, mostly on the Argentinian side. And the other language family is the Sasic language family, which is part of the Caucasian family, which is spoken by a few thousand speakers in remote villages somewhere in the middle of the Caucasus, where there's basically not even roads to go there. We choose those. At the time when we were working on that, there were people researching these language families with classical linguistic methods, were there as long-term guest researchers at the Max Planck Institute for Evolutionary Anthropology in Leipzig, and our collaborator there, Michael Züso, had arranged with those guys that they would actually look at what we produce from our stuff. So this is the data again. This is a little bit what these languages look like when you align them. So they actually, so these language family, so the Caucasian language family, Sasic, is something that linguists like to work with because it's the language family that has the largest number of distinct phonemes. If you would have a specific letter for every phoneme, so meaning distinguishing sounds, you would need an alphabet with 168 letters. So this is the extreme case. The other extreme is Hawaiian, which I think has 13 phonemes, or 14 if you count the glottal stop or something. So there also you find the usual patterns. So there's a lot of things that are identical or almost identical. You find some. We find essentially the systematic sound changes that we were supposed to find, and this is basically what we got out in terms of pairwise cognitive assignments between these languages. There is a large part of the pie that we call trivial, because those are actually words that, give or take one vowel, are actually identical. So those are the cases that are too easy to need a computational method. So this the yellow thing is the things that everybody would say, why do you need a computer? This is idiotic. But the interesting, useful thing is that we basically got quite a number of non-trivial correct answers, and compared to that, so of the non-trivial cases, we got about 90% correct and 10% is crap. And the really interesting part is the questionable ones. These were the ones that we got out of the data where the linguist said, I have to think about this. This is actually very interesting. I have to go research these things. And to my knowledge, they wrote 2-3 papers about these examples that we uncovered here. And what you also see is that the numbers get a little bit better if you, instead of just look at pairwise comparisons, you look at comparison of multiple groups, then you also get this partly correct group where some of the things that are in the alignment is something where the linguist says, yes, this is true. And some other thing that is in that multiple, I don't know, this one is wrong, this shouldn't be here. Or this is a loan word that doesn't count. So then you can use this data because you have a long alignment of this thing, you can just concatenate it and use standard methods of constructing the tree, which luckily gives the tree that the linguists working on this language group are actually interested in. And we also got the sound changes right, and blah, blah. So you can do the same thing with Gaikuruan. And then essentially we noticed where this doesn't work so well, because actually a lot of the sound changes that you observe are not like Grimm's law, like the P to F, that is just universal anywhere in the world. But a lot of the sound changes are actually position dependent. That's one example is the disappearance of an F before an I or an E in Latin into Spanish and Portuguese, or the instead of an LI in Latin. This is regular sound changes that require that you look at least 2 letters, or that you look at whether you are at the beginning of the word or not. So the obvious idea for that, for doing that, or for dealing with that is, so in principle, every linguist will tell you where you should look at the syllable structure of a language. The problem is nobody knows what the syllable structure of the language is without studying it in detail. And this is a kind of approach that we want to be able to do with languages where we actually have no clue about. Right? Otherwise, so the whole idea is of this whole exercise is you can go through a large number of languages and point out the interesting examples or the interesting questions to linguists where the machine doesn't make a clear distinction or a clear cognate assignment, or it produces a clear phylogenetic assignment in the first place, right? So those where you want the domain expert to spend money and time on, rather than go through lots of examples that the computer can resolve all by itself. So the question was, how can we improve the scoring model for our alignments, and therefore also the rules for the sound changes, which is what underlies the scoring model of the alignment. And the kind of obvious way that we came up with is, well, then let's just score alignments with overlapping bigrams. And so you just explicitly annotate the beginning of a word and the end of a word. And it turns out that this actually already captures a lot of the position dependence, not everything, but a very large fraction of the position dependent sound changes you actually get right in this model. And it also improves a lot on distinguishing between cognates and non-cognates. And now you can actually just really do this based on the score distribution of the alignments at the end. So you get very nice. So for Indo-Germanic, this looks pretty good. You're already in the raw unigram type alignment that I showed, or scoring that I showed you before. You get a near perfect distinction in terms of the alignment score between cognates, so words that are actually related, and words that are unrelated from the same meaning. You basically see that this is the unrelated peak if you just compare it to the scoring distribution of unrelated words that you pick at random from different rows of the word list. If you look at languages like Guy-Korean, this distinction is actually pretty shitty. Right? We get a peak for the near identical ones, and then we get a peak smear. So all the interesting ones are essentially somewhere in here, and we cannot distinguish them. And that basically has to do with the fact that Guy-Korean has a lot of sound changes that are either at the beginning or at the end of the word, and it stays identical in the beginning, and that kind of screws up your scoring model. But it gets a lot better if you look at the bigrams. It doesn't get as nice as Indo-Germanic, but this is already something that you can work with, right? So everybody would cut here, and that's also what makes sense compared to talking to domain experts. Yep.
So basically, given that you're using bioinformatics methods, you want everything to be a sequence of symbols, right? But that's not a sequence of sounds, so you go to the bigrams, etc., to try and make that a bit better. But in principle, you could do this all at the level of, let's call it frequency Fourier analysis of the sounds themselves, right? In other words, Porto y Porto,
you
right?
could in principle, except you very quickly don't get enough data.
You mean in the sense that there are just not enough recordings of sounds around?
Yeah, they're just, for most of these languages, you don't really have much more than a more or less elaborate word list that some missionary collected 100 years ago or something.
Yeah. But if it did exist, it probably would be better, I would expect, right?
Yeah, so, I mean, you could, so these are all things where this obviously gets a lot better the more data you have. And because then you can be much more conservative in what you take in. But you have, even worse than in bioinformatics, you have a data quality problem here. So just as a side remark, I don't have slides for this. One of the problems we had in getting this particular work published is, yes, but who says that a K in this word list is actually the same as a K in that word list? And actually, you use inconsistent phylogenetic, inconsistent phonetic encoding, because everybody knows that this C in this language is written X in the other one, or vice versa. So we actually did quite a bit of statistics showing that as long as the encoding in one color for one language is consistent, so it's self-consistent within one language, so they didn't use 3 different symbols for what's supposed to be the same sound. As long as this is self-consistent, it doesn't matter, because it basically then the inconsistency in the encoding will essentially just show up as a sound change that's not really a sound that change, a difference in the encoding. So there's lots of issues like this, and I mean this also goes back to can you use orthographic data instead of really sound encoded data, because the orthographic ones are much easier to get to. Basically, you can just say, okay, I want these terms from the English description of what the meaning categories are in the word list, and you just pick them off a dictionary. We actually did that for Indo-Germanic. It works just as well as the sound encoded data, basically with exception of Irish, and there was one other example that I forgot, but basically everything else is close enough to a phonetic transcription of some stage of the language that you actually get the right phylogeny out at the end. So there's a lot more also stability in this data. And this is also something that, to my surprise as a bioinformatician, but not to the surprise of any of our linguist collaborators, was a very hard sell to the linguistics community, is that it's already sufficient that the data are right most of the time. That you have some erroneous data in these lists, and that you don't spend, going into the literature for checking every entry. Doesn't matter, because the errors are rare enough, or they are completely systematic. The completely systematic one will show up at the end. The ones will just get squashed out in the scoring model, and you lose one or the other cognate in one or the other language. And as a bioinformatician, you're super happy to live with getting stuff 90% right. So, okay, this also works. So then one of the questions that people had in this field is, there was a long, basically religious war on whether Matako and Kaikuruan are related to each other, or whether those are actually two independent lineages. So what we did is basically we used our data to see if you just compare words with the same meaning, and you look at the alignment similarity versus you just pick words at random from these word lists, and then you see, okay, there is a big peak above the background for Kaikuruan. So obviously Kaikuruan has a lot of coherence, so there's much more similar words with the same meaning within this group than we should expect. So we believe that this is one coherent group. This doesn't look as nice in Matako, where the languages are just much more different among themselves already. But statistically speaking, this has a very high p-value, that there is actually a non-trivial area under the curve. But if you compare Matako versus Kaikuruan, that exactly looks like a random comparison. And this same thing is basically shown here also with a KS test to check whether the distributions actually are different. And then you see a very nice square showing that, yes, there is always a difference within Matako. There is always a difference within Kaikoru, and between the two there is actually not much. There is only those two entries you have to explain, and this is probably a language content effect because Pilaga is apparently sort of the most common, most widely spread out language there. So negative result there, we cannot prove that these families are related, but what we basically can say, you can do whatever you want with these word lists, you will not get a signal out of that. So given on the word list data, you cannot prove a phylogenetic relationship between these two languages. Okay, who cares? So you can also play that. This is data from Danmai Bhattacharya at the Santa Fe Institute, who did a related study several years later on Turkic languages. And they just very nicely showed if you just plot the similarity. So within every block, the X and the Y axis is always one language. And you just compare across the whole word list, and then you aggregate the similarity, just basically the alignment score between all the words. And what essentially you see is, well, there is some terms like ash, where all the Turkish languages use the cognate term because all the words are very similar. then there are some subdivisions where you get essentially two different cognate groups, two different groups of words that are used, for instance, for belly in Turkic languages that distinguish, as it turns out, major language group, or three actually. And then you also have very weird effects that there is one language that likes to use the word for ash for the term for all, for everything. And it doesn't use the original term, so the ancestral Turkic language term for this. What the reason for this shift is, for this semantic, it's probably a semantic shift because it really looks like the word for ash. How that happened, nobody knows. Probably somebody wrote a paper about it to tell a story on that. But there is several effects of that, where you actually, so one of the uses of this, that in particular Tanmo is working on, and we're playing around it with this a little bit. So you can actually use this data that you have on cognacy to actually also look at how and when the words change their meaning. But I don't want to go into that. We just mentioned that. And then there's the fundamental question: should I shut up, or how am I doing? More or less, so I can do that very quickly. If you, the phylogeny is almost finished, so I just gloss over these limits of phylogeny thing and just make a couple of remarks on that. So the idea there basically was, this is maybe interesting because it has to do with, can we actually, does it actually make sense to use this data for making phylogeny? This is also sort of one of the criticisms that you often get. Well, you don't have a mechanism, you don't know that the things that the data that you observe has to do with the underlying causal mechanism. So how can you reconstruct a genealogy? So what we did basically was just to ask, well, if I have transformed data, so if I just have my similarity data of some representation of my process, under what circumstances can I actually use that to get the correct phylogeny back? And the first remark is basically just, this is not a trivial problem. So just imagine phylogeny looks something like this. And all the examples always have to do with you have a couple of lineages that evolve much faster than everybody else. In there, this is known as long branch attraction in phylogenetics. So now if this is what the true process is, and you observe something like sequence similarity, which will transform like in a sort of saturating curve, right? Sequence similarity cannot be more you can never be more different than two random sequences. So if you have a signal that at some point will saturate, what you get then is measured distances that if you try to infer the phylogeny from them, you just get a completely wrong answer. This is basically the long branch attraction effect. What it basically does, it says, well, the two very similar things should actually be close together, and the two very different things should be somewhere else, right? So you get a picture like this that pulls these two together. And the question is, can I see that my data are actually not data that I should do phylogeny with? And the other question is, can I correct it? Mathematics tells you can reconstruct the trees from distance data. Exactly, your distance fulfill a condition that's called additivity. I'm not going into details what that is. Basically means that for any four taxa, for any four distances between any 4 points have to satisfy certain conditions. Um, the question is, so it's easy to recognize that your data do not satisfy this requirement. The question is, can you transform them back? Well, under the assumption that what you see is just a monotonic transformation of your data, it turns out you can. And the trick is actually quite simple because there is 3 reconstruction methods that are guaranteed to give you the correct answer if you feed them with additive distance data. So you can actually use these phylogenetics methods that have this property that they are consistent for additive distance data as a means of measuring how far away your input data are from being additive. What you do is you just take your raw data, you throw them into this method like neighbor joining. This will give you a tree with branch lengths, and then you calculate the distances again, and you just check how big is the difference between the distances that you threw in and the distances that you get out. And what you do then is then you say, okay, this doesn't match. Can I find a monotonic transformation of the distance data that actually makes the transformed invariant under my phylogeny construction method? So if I take my original data, I transform them, then I do the phylogeny reconstruction, I get something that's the transformed data again. This obviously gives you also a minimization method. It basically says adjust the transformation so that the discrepancy that you generate by doing your phylogenetic method becomes as small as possible. This is basically what's written here. And the nice thing is, at least on simulated data, that actually works. So this basically just shows that you get the right parameters for the transformation function that is used and hid from the program out by just minimizing this discrepancy. So yes, you can use data where you don't know the details of the underlying model, as long as they are monotonic transformations, which they usually would be, where you actually don't know what that transformation is. You can actually take the data, optimize the transformation function, and then reconstruct your phylogeny with the transformed data. And the nice thing is this actually explains a posteriori why certain so-called non-alignment distances so there's a field in bioinformatics that tries to do phylogeny without calculating alignments first. So doing sequence comparison basically by index-based, so suffix array-based methods or something like this. And some of them work well and some of them don't work at all. And it turns out you can actually show with the same machinery that the ones that work are exactly the ones that reconstruct the additive genetic distance that you should actually count. And the ones that don't work are the ones that just produce other distances that do not have this additivity property. Let me forget this. So very briefly, chemistry. What we looked at is a data set that contains essentially all the chemical reactions and all the chemical substances that have been published since about 1800. So the fortunate thing is in chemistry, people have sort of a little bit of the stamp collection mentality. So until the 1980s, there were big book series for organic chemistry, Beilstein's Handbook of Chemistry, which in the last printed edition was, I think, 120 volumes or something like this. And Melin's Handbook of Inorganic Chemistry, which was supposed to be a collection of essentially all the knowledge about individual substances and the ways to synthesize them that has ever been published. In the 1980s, with computers becoming big enough to actually store that amount of information, at least on what was then a supercomputer, with big towers of disks and tapes. These data were actually transformed into electronically accessible data. So this is how you can have access to that. In principle, in practice, it's very difficult to get access to that because as opposed to the model in biology where the community decided in the 1970s that whenever you publish any biological sequence, you have to deposit it in a central repository, which is run by the NIH through NCBI, and there is a European mirror through the European Bioinformatics Institute, and also a Japanese mirror. So these three big countries basically decided we will pay for access to this repository. There's nothing comparable in chemistry. Instead, in chemistry, chemical industry decided we will have a foundation that will do that to make sure that all of the chemical industry community has access to that. And there's also access to that for academic institutions, but it's not free. It's actually a pay-per-view type of access. So you pay per individual query. It's very cheap per individual query, but very cheap means, this is like sending an SMS or so for academic institutions. So you don't want to do that for querying 50 million reactions. So nobody could pay for that. Luckily, and the really bad thing at face value is that the chemical industry actually decided to move this foundation under the umbrella of Elsevier. So Reaxys, the institution that owns this data, because they essentially own the copyright of the original printed versions of this handbook, is Elsevier. But it turns out the Reaxys Foundation they are actually not so bad. You can have a collaboration agreement with them, which just takes essentially forever to actually make work and really get the access in the way how you need it and so on and so forth. But people there were really helpful. It's basically just once you go, you get through all the legal red tape and finally have the collaboration agreement signed, and then find out that since we were apparently the first partners who needed access to everything, to actually make their system work to give you everything was not so easy because you cannot just dump everything. So then the thing will basically say, illegal access and show you the finger. So you have to write elaborate scripts that download the stuff in small but not too small chunks. So at the end, you get this data, and the guy who was really instrumental in that is Guillermo Restrepo, who is a Colombian professor who was visiting my lab for 3 years as a Humboldt Fellow and is now at the Max Planck Institute, and my friends in Vienna. Guillermo is the guy who's mostly interested in the history of chemistry part. What we looked at is, well, something very simple. What is actually the pattern by which chemists developed or explored chemical space, the universe of substances that we know? And the first thing that you note, well, there is this kind of more or less exponential growth in the number of substances that were discovered. If you look at the data, you also notice there is a very strange dip around the wars, which actually doesn't fit well with what people were always thinking and claiming, which is, the war efforts put so much emphasis on chemistry and blah, blah. In reality, of course, it didn't. It put a lot of emphasis in producing a few chemicals that you could weaponize, and essentially sucked up all the resources for that. So if you actually look at what this did nominally to the field, It's basically the war put you back about 30 years. And the effect was particularly pronounced at World War I, and this you can actually corroborate with historical sources, because chemistry at that time was very much a German science. Almost everything was published in German, and with Germany losing the war, a lot of this basically just of this whole infrastructure of chemistry research was something that essentially disappeared. There is a rebound effect after the war because, of course, some stuff was going on during the war, but it also couldn't be published because you didn't want to, disclose your new discoveries to your enemies. So there is a part of, you get part of a rebound effect that basically comes from catching up with things that happened during the war where you had resources after the war, but it's actually not true that you had a lot of additional resources immediately after the war to do chemical research. You also find things like this, which is just a stupid data artifact. That's an error in the database where for some chunk of data that they recorded, they only put the substances on the product side, but not the edicts into the database. And since there is a lot of synthesis from natural substances and things like that, a lot of substances are missing. So there's all sorts of weirdnesses, even in this database that was like collected and curated to death, you would think. It's just incredible how much things you find in there that make no sense at all, even though every single entry went through 2 human curators. And this is not at all criticizing these guys. They do a fabulous job, because if you would like to, you would try to get this information out by automatic text mining or actually image mining techniques from the printed literature, it would be much worse with the technology that we have available.
The thing is that what I was kind of was worrying about there is like, how can the number of substances be so much less than the number of reactions? But the way you're using is educts, and it's basically the substances are just
no, but so
it's kind of redundant almost, right?
So the scatter down here is, and why one sometimes overtakes the other in the old days, is because this is not cumulative. This is actually discovery per year. Mm-hmm. So that's the increment, not the total that's known. I mean, which is kind of clear from the fact that the curve is not monotonic. So what you have is that, and sort of so there's lots of weird data artifacts, and some of that also comes from the fact that, so you have fewer reactions than substances, because in the last years, you have a lot of these combinatorial chemistry efforts where you produce in the same pot multiple substances that you only separate out afterwards. And there's many effects like these that you can read off the data.
Yeah, what I was thinking is that if you got A, B, and C, that's 3, but A plus B, A plus C, B plus, so you have exponentially more reactions and substances, but on the other hand, you're putting the product, the edict, right,
but the
interaction as another substance.
This is to a large extent not how it works, because if you look at what is the composition of edicts that people throw in, it's usually one rare, relatively new substance plus a reagent that was already discovered somewhere down here. So mostly the reactions are something recent or maybe even something old, gives one new product, and both the reagent and the byproduct of byproducts is actually stuff that has long been known and usually falls into the class of sort of the commonly used, usually used substances. So in that sense, chemistry is very conservative. you do the same type of reactions, the same schemes, all over on many, many substances. And a lot of that, of course, is driven by the relatively systematic exploration of certain substance classes that are of medical interest by the pharmaceutical industry. So they are really among the most conservative that you could think of in terms of exploring new things. You basically take substance classes and make additional variations on those, because basically nobody wants to work with completely unknown substance classes. You don't know whether the synthesis works there. You don't have good predictors for structure-function relationships. Nobody knows whether they are actually druggable, so whether you actually do get them into the cells and so on and so forth. So a lot of these. A lot of the stuff that you see here is sort of tiny variations on a theme. Mm-hmm.
Do you know what would be the relation between reacting substances to think once again?
You would in an artificial chemistry setting where you get to basically play with, we make new reactions and new substances, you would also get this kind of collinear system, because essentially if you have different, so the way how this is counted is if you have different either, that also means a different reaction. So you don't boil that down to, yeah, so this is why they're more or less the same. But you would, you know, if you explore in this combinatorial way, the growth would be much, much faster, because you would not be constrained to using one new substance to just some standard reagents, out of many, of a few dozen that's usually used. But you would just try to combine anything if you do that naively, and so the exploration rates would be much, much larger. What one cannot see, but if you go through a more analysis, what you find is that there is actually different regimes in there that are in part determined by the variance, and in part by differences in the slopes. What comes out of that is that you have a first phase which had a lot of variance, and actually the slope is also a little bit different from the rest if you use techniques from time series analysis for the increments. And it turns out this phase ends about 1860, roughly. And this is dominated essentially by doing inorganic chemistry. And then you get a phase that goes until the 1960s, 1970s, which is dominated by organic chemistry. And what has paradigmatically changed in chemistry there, and that also led to the quick rise of organic chemistry according to historical accounts on chemistry, is the advent of structural theory. So when people realized that in particular organic molecules actually have a structure that you can essentially understand as a graph, and there is a lot of regularity between isomers and regular lines of substance classes and so on and so forth, that you basically can go and systematically explore with the same types of reactions. This basically sort of dominated this middle part here. And if you look at recent time, then there is again a paradigmatic shift, because most of the newly reported substances are actually organometallics, so complexes of organic molecules with usually transition metals, which are used as catalysts and so on and so forth. What we don't know is what really was the trigger for that. In part, probably it was the rise of biological chemistry, because at least this transition coincides with the rise of journals that specifically deal with biological chemistry, and it's actually now not the Journal of Organic Chemistry or the classical sort of core organic or inorganic chemistry journals that report most of the new substances. It's actually journals with titles like biochemical engineering, pharmaceutical, synthetic chemistry, things like those. Those types of journals are the ones that now report over the last years report the largest number of new substances, and this was actually a fairly sharp transition also in the way how the literature behaved that may have been triggered in some way by the advent of basically biochemistry and the merging of biochemistry and genetics. I think I stop here instead of drowning you in a few more data. And sort of as the overall topic or the overall take-home message, there are many interesting questions, at least for me, in cultural societal systems that we actually can answer using data that are out there, essentially the reasoning that we are used to from the natural sciences. It does open research areas that people haven't really thought of in that way. So there's an effort to sort of formalize a little bit what computational history could look like. So computational history in general could look like both in practice, also in concept with people at Arizona State University and the Max Planck Society. And I should emphasize the idea is that this complements what is done in the humanities. So obviously we don't want to write to construct machines that interpret poems or things like this, right? This is not, the point is not to supersede what scholars in the humanities are doing, but to open new perspectives and to allow to make use of the wealth of data that is out there to answer questions about human society, human culture, about human evolution at an academic level, and not leaving dealing with this data and making something, namely money, for the Googles and Facebooks as the only people who deal with it. Thanks.
Thanks to Peter. So questions, anybody has a question or a comment?
It's very general. Well, first of all, thank you for this wonderful talk. What is the near future of all these field or related fields and the middle term future? You mentioned at the very end Google, Facebook. What about this fuzz word like artificial intelligence, machine learning? How do you see and this eternal war between the humanities or the exact sciences and the hard versus soft sciences?
Yeah, so I mean,
in terms of collaborations, for instance.
So I think there is a large field where this can very meaningfully and fruitfully coexist, as is the case now in the life sciences. So there's not that many people left, I would say, in the medical sciences, in basic research, in the life sciences, who think computers, bioinformaticians, and data analysis is stupid and we don't need it. There are a few around, but they're basically, I would say, a dying species, a species that is going to be extinct soon. And I actually envision that we will have you will get, and this doesn't mean that everything that has to be done in biology or every interest in biological research has to be big data, machine learning, and needs a bioinformatician, right? It basically just really, genomics is a field that just wasn't there 20 years ago because there was no technology to measure that and no technology to analyze the data if you could have measured. So I think it's just a natural progression that as we get a lot more data on the systems that are of interest in this case to humanities, that you will also develop computational techniques to deal with them. And in the moment, at least, we don't have any other methodology than the one that we essentially borrow from the natural sciences to deal with this data. We don't know to do anything with this data except for regularities and look for exceptions beyond these regularities, which is basically the classical approaches of both machine learning or classical statistical data analysis. So in that sense, I think machine learning is really just an extension of the statistical machinery that has been used anyway, and it's used for exactly the same purposes that we used sort of more model-based statistics in the past, because we didn't have sufficiently powerful computers to actually do deep learning. It's not like nobody has thought about building really, really large multi-layer networks 30 years ago. It shouldn't do anything with them because it would have taken forever to calculate or to train them. So now we can do that. And so, I mean, this is really very much a personal opinion. I think what's sort of all these there's a political hype now about machine learning, AI, and whatever. And this will go away like any other fad, because what will stay is that these methods now become powerful to do things that you couldn't really do with classical statistical approaches, because we just don't know what the underlying models is or should be for many of the things that we analyze. And this really is of these methods, right? You need to have less of an idea what is the structure of your data. And so from that point of view, I think they're super useful and they will be used in all these fields a lot. But my hope is that as we learn more about the structure of the data, we will actually go back to more model-based approaches just because of interpretability of the data. Right? So, I mean, if you can perfectly predict something that may be enough for you, but you still don't understand the way it works. And this is a little bit the kind of the issue, right? So in biology, in biology, there's also this thing. I can understand things by just taking them apart. But in chemistry, the level of proof is, you know that you have the substance that you think you have if you can actually build it, if you can actually synthesize it from scratch. And the whole program of synthetic biology, in part, is basically built on this credo. We understand stuff if we can actually build it. And I think this is useful because from a point of view of technological applications, we actually want to understand the things that we stick together, at least sort of, so that they don't do many things that we didn't anticipate.
So the way I see your three first parts of your research is that you're actually doing some kind of interdisciplinary work, in the sense that there's some question posed by the humanities, and you're trying to develop an answer based on your techniques or your knowledge about these methods. Do you see any future in which there's actually a transdisciplinary approach to this issue? for example, in language, in which the question it actually is created by a community of disciplines. So, for example, if you find that the process by which language evolves is similar to how organisms evolve, what can you say about the commonalities of those processes?
So this is actually, this is indeed something that we now is is not my research group, but is actually a large group of research groups coming together, in particular at the Santa Fe Institute, with people from the history of sciences, linguists, physicists, computer scientists, or people turned computer scientists like myself, where we try to do exactly that. And this always has kind of two aspects to it. So from my experience, the transdisciplinary approach is always very fruitful at the conceptual level. Once you go down to the nitty-gritty detail of actually doing something on a concrete data set, you have to work with very concrete methods that just have to come from somewhere. So I don't know of an example where you really genuinely developed a data analysis method completely from scratch. So, and this also ties in with actually data that are not mine, but studies that my friend Manfred Laubicher at ASU was doing on innovation in science, in particular in the life sciences. What he found is that most of the conceptual innovation in immunology, in evolutionary biology, they always come from methods transfer and new experimental techniques that allowed you to do to ask new questions. And this always, at least in all the cases that he studied, that he found in his computational analysis, this is always also associated with kind of unusual contacts and collaboration between people from different subfields, and apparently the kind of enabling mechanism is that you suddenly get a new toolkit to work on stuff, and this actually then also leads to a conceptual how you look at the problem. We don't have hard enough data to say this is how innovation science works, but at least it's a plausible narrative for which we have a good handful of well-documented examples. And if this is how innovation goes in science, I mean, this is basically then also kind of a recommendation of what kind of projects your funding organization should fund, and which projects are a complete waste of time because they only add data to things that you already know. I mean, if the interest of your funding organization is funding innovation rather than completing a knowledge base, which is also a value in itself, a lot of the things cannot be done without actually the data being available. So I don't want to denigrate at all the kind of very incremental contribution to science. It's just a question of resource allocation, right? So how much completion to how much kind of more high risk, maybe crazy, but also more high gain type of research we want to fund. I don't think you can predict the innovation, but I think what you can predict is what is the probability that project X does more than just add data to things that we already know.
Any other question? Okay, let's thank Peter again.